Dynamic braking systems. In this presentation, we're going to be looking at the parts and components of a dynamic braking system, the concept of operation, common control circuits, and finally a summary of points. In order for us to have a dynamic braking assembly, we need to have a standard starter, typically a time delay relay and a contactor rated for DC voltage, and finally a rectifier. The premise of the operation is that after three-phase AC has been removed from the stator, when we press the stop push button, DC voltage is immediately applied while the motor is still turning. And now on a three-phase motor, that means that DC is applied in its two polarities to all three terminals. So in this instance, we have three contacts, 1, 2, and 3 here, and perhaps the negative is applied to this one and the positive applied to both of those. It kind of depends if it's a Y-wound motor or a delta wound at times, but not of significance for us at this point. Now, the magnetic field established by the DC source being applied to the stator is static. It's not rotating. And so what that means is that the rotor bars continue to turn due to the inertia of the mechanical load driven. The rotor bars cut the lines of flux, causing an EMF to be induced into them. The induced EMF causes current to flow in the bars, which develops its own counter torque, which then opposes the stationary DC stator magnetic field. And this is in line with Lenz's law. The resulting counter torque force developed in the rotor slows the rotation of the motor. Interesting enough, as the motor slows, less braking force is generated because the speed at which the rotor is cutting those lines of flux is reduced. So as the rotor slows, we get less and less braking force, which makes this an exceptionally smooth stopping type of system. When the motor is running, we have A, B, and C three-phase applied to the stator winding, whereas as soon as we apply dynamic braking, we apply the full DC voltage across the three-phase stator winding. I've used 810 volts DC as an example, as this would be the full wave bridge voltage for a standard three-phase system. We can use this type of braking on three-phase motors and single-phase motors. And it can often also be applied from something called a variable frequency drive, instead of having to insert a completely separate rectifier and uh, dynamic braking contactor. Dynamic brake systems can be controlled by a time delay on energization relay or a zero speed switch. We're just going to look at the time delay on energization circuit. Here's the typical circuit. We have a rectifier over on the power side. We have a time delay on energization relay. And finally, we would also need to have a contactor that was rated for DC voltage. So not the coil, but the contacts themselves. Let's take a look at its operation. The first thing we do is we press the start push button, which energizes the M coil. The M coil is what changes the state of the power contacts and allows the motor to run. At this point, the motor is running in whatever direction has been predetermined. When we press the stop push button, at this point, the M coil de-energizes, which opens the contacts for the three-phase applied to the stator, and it energizes both the timing relay and the DB contactor. Now, what this does is all of these contacts change state at the same time. And what we see is that now we have voltage applied to the full wave rectifier, and this is a single phase rectifier. And then we have the DB power contacts closed to apply that DC voltage to the motor stator. So now what we have is DC voltage being applied through the full wave rectifier to our three-phase motor. And now the motor is braking, the speed is slowing. Now we have a timer set, and this one isn't as exceptionally important that we ensure that the time is set precise because even when the motor reaches its stationary position, the contact will open and the system will be de-energized, but honestly, not really a big problem. We said once the motor reaches a stationary position, there's very little braking that is being applied. And that's because there's very little lines of flux being cut by the rotor bars. So this one will not cause the motor to automatically reverse direction in any way. And once the whole system is de-energized, you see that the timing relay contact returns to its normal state. Dynamic brake systems are also known as DC injection braking systems. They are used to very quickly slow the rotor by applying DC voltage to the stator windings after the AC has been removed. They create a static magnetic field that is not revolving. The rotor bars cut the lines of flux, and oppositional or counter torque is then created, which slows the motor. Now, higher DC current will then result in a larger magnetic force and stronger braking force, thereby slowing the motor faster. No rotation of the motor would then equal zero braking force by the DC injection system.